In this lesson, we're going to look at polynomial equations and how to solve polynomial equations. So before we start that, we're going to look at the different forms that you've seen polynomial functions written in. So we've seen it in standard form for quadratic, cubic, and quartic. We've also looked at them in factored form for a quadratic, cubic, and quartic as well. What we're going to be focusing on is how to get from the standard form here over to the quadratic form so that we can look at where the x-intercepts are, what the graph would look like, and how to graph a polynomial function. So let's think back to what the word solve means in polynomial equations first. Okay, so why is it important to solve polynomial equations? Well, it's important because when you're looking at a polynomial equation, the word solve means to find the roots or x-intercepts or zeros of the corresponding polynomial function. So for example, if you have p of x equals x plus 7 times 2x minus 1 times x plus 5, the first statement here represents the polynomial function. Now, if you wanted to figure out the x-intercept zeros or the roots, what you would need to do is set the polynomial function equal to 0. And then once you have it equal to 0 in factored form, you can actually solve for each of the different x-intercepts or roots. So for example, in this case, we have a cubic function with roots at x equal to negative 7, x equal to a half, and x equal to negative 5. So for a polynomial function, y equals p of x, the roots are determined by setting y equal to 0 and then solving the polynomial equation p of x equal to 0. If a polynomial equation is factorable, the roots are determined by factoring the polynomial, then setting each factor equal to 0, and then solving each factor. If the polynomial equation is not factorable, then you can estimate the roots by looking at the graph. Okay, so some quick steps for you to solve a polynomial equation. So your first step is to set the function equal to 0. And then factor the function or factor the expression just like we did previously. So use the factor theorem to figure out a factor, and then use long division to factor it further. And then your last step is to solve for the roots the exact same way we did in the past. Okay, in the first example, it asks us to solve by factoring. So we have 2x cubed plus 3x squared equals 5x plus 6. And so in order to actually factor this, the first thing we want to do is get everything on one side. So I'm going to rearrange it so that everything's on one side. And so I get 2x cubed plus 3x squared minus 5x minus 6 equals 0. Now, in order to have this in factored form, we need to use long division. And so we're going to look at the expression on the left-hand side and try to come up with a factor of 6 that will make the left-hand side equal to 0. So the factors of 6 that I know are plus or minus 1, plus or minus 2, plus or minus 10, plus or minus 6. And so I'm going to use positive 1 to start, and if positive 1 will give me a result of 0, then I know that x equal to 1 or x minus 1 will be a factor. So if I plug in positive 1 here, I get 2 times 1, which is 2, plus 3 times 1, which is 3. So far I have 5. Minus 5 times 1, which is minus 5. So far 5 minus 5 will give me 0, minus 6, and so that gives me negative 6. So I know that x equal to 1 is not a factor. So let's try x equal to negative 1. If I plug in x equals negative 1 here, I get 2 times negative 1, which is going to give me negative 2. So I'm actually doing negative 1 cubed, but I know negative 1 cubed will give me negative 1, and that'll multiply by 2 to give me negative 2. Then I have negative 1 squared, which is 1, times the 3 is positive 3. So now I have negative 2 plus 3, which is 1. Then I have negative 5 times negative 1, and negative 5 times negative 1 will give me positive 5. 1 plus 5 is 6, and then 6 minus 6 is 0. So I know that x equal to negative 1 is going to give me a result of 0. So what that tells me is p of negative 1 is equal to 0, and so what that means is that x plus 1 is a factor. So what I'm going to do is long division the way we've seen it all along. And so here I've done the long division on the side. So I'm dividing x plus 1 into 2x cubed plus 3x squared minus 5x minus 6. And once I've done the entire long division, the quotient I end up with is 2x squared plus x minus 6. And so what that means is so far my factored form now looks like x plus 1 multiplied with the quotient that I had, which is 2x squared plus x minus 6. And so it's almost completely factored. I have a quadratic trinomial inside the brackets. still. And so if I factor that like a complex trinomial, like I've done since grade 10, then I get the factored form of the cubic equation that I had. And so my three factors are x plus 1, 2x minus 3, and x plus 2. And so if I solve each of those factors equal to 0, I get x equal to negative a half, x equal to 3 over 2, and x equal to negative 2 as my three factors, or sorry, as my three x-intercepts. And so what this means is if I take any of these values and I plug it into the left side, and I plug it into the right side, then my left side should be equal to the right side for all three of those x-intercepts or roots. Okay, in example 2, we're asked to sketch a graph of the function g of x equal to 4x exponent 4 plus 6x cubed minus 6x squared minus 4x. And so if we think back to how we graphed polynomial functions in the past, we looked at d Lexy, Delexy. And so if you think back to what this little acronym stands for, it means we're looking at the degree of the polynomial, the leading coefficient, whether it's positive or negative, the end behaviors of the function based on the degree and the leading coefficient, any of the x-intercepts, and then the y-intercept as well. Okay, so some of the information we already know. The degree of the polynomial is degree 4, and the leading coefficient is positive 4. And so what this means is this is a positive, this is an even function with a positive leading coefficient, which means the graph would sort of look like a W. And so the end behavior of the function would be, as x approaches positive infinity, the y values would approach positive infinity as well. And as x approaches negative infinity, so as it gets smaller, y should be approaching positive infinity as well. It's an even degree function, so you should be expecting the same end behavior. Okay, and because the leading coefficient is positive, it should be opening up. Now the problem is, I have all that information, but I don't know how to graph this. Okay, in the past, what we've had is the expression in factored form, or the function in factored form, and then once it's in factored form, we knew exactly where the x-intercepts were, and then it was also easy to solve for the y-intercept. In this case, it's also easy to solve for the y-intercept. All I need to do is plug in x equal to 0 into my function, and I should be able to figure out the y-intercept. So why don't we do that in the meantime, and then we'll come back to the biggest problem, which is not knowing what the x-intercepts are. Okay, so we can solve for the y-intercept in this case. Just because we don't know the x-intercept doesn't mean we can't move on and try to solve for the y-intercept. So I can do that by setting x equal to 0. And if I plug in x equal to 0 into my function, that means g of 0 is equal to 4 times 0 to the exponent 4 plus 6 times 0 to the exponent 3 minus 6 times 0 squared minus 4 times 0. And if I simplify that, what I end up with is 0. So that means my y-intercept is at 0, 0. So there's my y-intercept. Now I just need to figure out where all my x-intercepts are. How can I figure out how to do that? Well, if I had this in factored form, maybe then I should be able to figure it out. So that's what we're going to do, and I'm going to do that lower down here. And so what I'm going to do is I'm actually going to try to figure out what the factored form of this expression will be. And so far I've just written it down. And so we're going to try to factor this. So first thing I want to do is recognize whether or not there's a common factor. With all polynomial expressions, the first thing you want to look for is a common factor. And in this case, the common factor is 2x. So I'm going to factor out 2x. And I'm left with 2x cubed plus 3x squared minus 3x and then minus 2. So there's my expression somewhat factored so far. Now the polynomial or the trinomial part that I have inside the brackets, I'm going to factor using the factor theorem, just like we looked at in the previous example. So I'm going to use the factor theorem, and because I know that this expression here, if I plug in x equal to 1 into the expression, I will end up getting a remainder of 0. Perfect. So since x equal to 1 will make the function equal to 0, then I know that x minus 1 is a factor. So since g of 1 is equal to 0, therefore x minus 1 is a factor. And I'm only going to look at this part here when I'm doing my factoring, so I'm going to use long division to do this. So I have x minus 1 into 2x cubed plus 3x squared minus 3x minus 2. And so this example really combines all the different concepts that we've looked at so far. We looked at long division, we looked at factor theorem, and we looked at graphing as well. So it sort of combines everything. Okay? And so if I do my long division here, so I need to figure out what I need to multiply x by to get 2x cubed. That's 2x squared. And if I continue here, I subtract and I get 5x squared minus 3x. So that would be positive 5x. And that gives me 5x squared minus 5x. I end up with 2x. So that would be 2. And I end up with 0. And again, if you didn't end up with a remainder of 0, then that means that you made a mistake in choosing your factor. Okay, or maybe you made a mistake in your long division. So far now, my function looks like g of x equals 2x times, my divisor was x minus 1, and my quotient is 2x squared plus 5x plus 2. And then finally, so far I have 2x as one of my factors, x minus 1 as my second factor, and then I have a quadratic trinomial as my third factor. This part here I should be able to factor more. It's just a complex trinomial. And when I factor it, I get g of x equals 2x times x minus 1 times 2x plus 1 and x plus 1. Okay, so there's the expression or the function in factored form. So now I can actually solve for my x-intercepts. My x-intercepts would be x equal to 0, x equal to 1, x equal to negative a half, and x equal to negative 1. So there's my four factors, or there's my four factors, and there's my four x-intercepts or roots. Okay, so if I go back to my little delexy thingy that I have at the top, I have x equal to negative 1, so I'm just listing it from lowest to highest, x equal to negative a half, x equal to 0, which means it's hitting it at the origin, and that's what we found for the y-intercept, so far so good, and then x equal to positive 1 has my four x-intercepts. Okay, and that makes sense. It's it's a quartic function, so I have four x-intercepts. So I'm just going to create a scale here. So I'll just use a scale of a half, so that's 1. So negative a half and negative 1. And if I plot my points that I know so far, I have my x-intercept at negative 1, at negative a half, at 0, and at 1. And I know I have a polynomial function that's going to open upwards, and it's a quartic function, so the end behaviors would be going towards positive infinity. And so because it's a degree, because I only have a degree of 1 for this root, I know it's going to cross through like a linear. I only have a degree 1 there, so it's going to cross through like a linear. Degree 1, so it's going to cross through like a linear. And then degree 1, so it's going to cross through. So there's my quartic function g of x. Again, remember, it was given in standard form, so we had to get it in factored form to figure out the x-intercepts. We knew the degree, we knew the leading coefficient, we knew the end behaviors, and we were even able to figure out the y-intercepts. So the key part here is figuring out the x-intercepts, and in order to do that, we had to get it in factored form. Okay, and that's pretty much it.